Hello everyone. Today I will present our work that has been accepted for publication in the proceedings of the 2021 International Conference on the Unmanned Aircraft Systems. The title of our paper is an Ellipsoidal-Polytopic based approach for aggressive navigation using nonlinear model predictive control. The work was developed by Mija Pereira, Walter Leite, and Guilherme Rafa. I and Guilherme are with the graduate program in electrical engineering at UFMG. I and Walter are with the Department of Mechatronics Engineering at UFMG. Guilherme is also with the Department of Electronic Engineering at UFMG. The presentation is divided into 6 main topics as follows. First, I will introduce the paper and right after define the problem that we are pursuing. Then I will show the main aspects of our proposed solution, and in the end I will present some results corroborated with a quadrotor UAV from numerical experiments, and draw the main conclusions of the paper. So autonomous motion systems, which can be a robot, a car, a UAV, has attracted the attention of society in general in the recent years. The majority of applications, such as search and rescue missions, involve navigation and cluttered environment with unknown obstacles. Typically, these vehicles must deal with earthquake scenarios, nuclear disasters, and forest rescues, as we can see in this image. Let's assume, for example, that a disaster has just occurred. So a distress call is then received by the firefighters for a person that is trapped in the rubble. Then the officers receive only a location point from a cell phone tracker, for example, that sends a GPS signal. However, this location is usually inaccessible or in danger of collapse, as you can see, for example, in this image. A person inside this accurate here and send a signal. The firefighter receives just a GPS signal. So autonomous motion systems that can help this officer, such as a UAV, a mobile robot, are very useful for this type of mission. Considering a UAV in the mission, the aircraft must navigate autonomously to the destination point while avoiding obstacles that have been discovered in real time. This means that the UAV must be capable of performing deviation maneuvers autonomously. But what happens when the available free space is not trivial? For example, when just a narrow gap is available, as is shown in the figure. Just this narrow gap is available to the UAV. Or to put it another way, what happens when the UAV attitude influences the success of the deviation maneuver? In this situation, the UAV must execute an aggressive maneuver. That means that the aircraft needs to fly fast, dealing with large linear and angular accelerations, while the UAV attitude is taken into account during the obstacle deviation. Deal with aggressive maneuvers require high-performance controller since extreme flight conditions is required to the UAV. Furthermore, the controller must deal with the collision avoidance requirements, taking into account the UAV attitude during the deviation maneuvers. Also, since aggressive navigation is required, representational singularities should be avoided in the problem formulation. An important design step in autonomous navigation scheme with obstacle avoidance capability is determining how to model the motion systems and how to model the obstacles. The kind of set used to represent them usually is a result of a trade-off between accuracy and computational cost. The symmetric sets represented by the intervals, ellipsoid, parallelotopes, and isotopes have simpler representation and consequently simpler set operations. However, their accuracy is dependent on the object type, and usually an approximation is applied to model arbitrary shapes. On the other hand, we have more complex set representations. We have the traditional and conventional polytopes and the recent class known as constrained zonotopes. Although constrained zonotopes provide exact set operation with smaller computational burden when compared with polytopic ones, the intersection between two constrained zonotopes is achieved just by linear programming. This is a problem for us because NMPC with collision avoidance capability concerns on the conditions under the intersection between the sets occur, which must be included in the optimization framework. As most of the motion systems can be modeled as symmetric sets, and obstacles usually have arbitrary shapes, we propose then a mixed representation, and we derived an algebraic condition that checks the collision between an ellipsoid and a polytope. Therefore, the main problem of our paper can be stated as the design of an NMPC for aggressive navigation of motion systems, modeled as rigid body whose dynamic equations are formulated on SU3. Usually these equations are obtained from the Newton-Euler approach as shown in equation 1, 2, 3, and 4. Here we see that the attitude of the motion system is parameterized by the rotation matrix R. Also, since the force F in the equation 2 is usually modified by the attitude of the motion system, that is, same to say by the rotation matrix, we can say that these four equations are coupled. The ellipsoidal set that represents the motion system is given by equation 5. Note that the set is defined by a matrix of physical parameters D, the positional key C, and the rotation matrix, being the last two time-varying states of the motion system. The matrix D is defined from the problem of enclosing the motion system, as illustrated in the figure, and this parameter is defined considering safety distance margins. The obstacles is modeled as a polytopic using the half-space representation given by the equation 8. That is, the polytopic is a result of the intersection of m half-spaces given by equation 6. Also, each half-space has a complementary half-space set, here we call S bar, defined by equation 7. Therefore, we derived an algebraic condition for collision check between an ellipsoid and a polytopic. Each is given by the following theorem. Basically, it states that if the function delta given by equation 9 is equal to 0, then the set Q and P are disjoint. To navigate safely, it's necessary to ensure that the ellipsoidal set Q is a subset of the free space during the prediction horizon and for all obstacles inside the sensor field of view. This condition can be guaranteed if delta L is equal to 0 during the prediction horizon and for all obstacles inside the sensor field of view. However, the constraint to L is considered hard and computational costly. And to improve this, we replace the constraint to L by soft constraint, considering the penalty function 13 at the cost functional. Finally, the NMPC scheme repeatedly solves this optimal control problem. The cost functional that is minimized is composed by the quadratic error of the position, the attitude error, the control effort, and the penalty function for the obstacle avoidance. This optimization is subject to the model of the system and to the admissible sets big X and big U. Note that the state that we are considering here, X, the state X, is composed by the position of the motion system, the velocity of the motion system, his attitude parameterized by the rotation matrix R, and the angular velocity represented by the omega. Okay. From numerical experiments, the proposed NMPC is validated with a quadrotor UAV. The figure illustrates this experiment in which the UAV must perform a point-to-point motion while avoid obstacles that are discovered during the flight. So the UAV begins here and has to accomplish to this destination point. The obstacles are discovered during the flight. So here is an example of a cluttered environment with unknown obstacles. This video shows the performance experiment. Here we have the top view and the lateral view of the experiment and the isometric view. I put here the aggressive maneuvers in detail and in slow motions that show the UAV flying through narrow gaps or narrow space. That is when its diameter is bigger than the length of the gap. So the only way that it can be passed away from the obstacle is performing an aggressive maneuver. One more time. In slow motion, the first gap pass. And another gap pass. About the conclusions, the results showed that the proposed NMPC is a potential solution to the present problem, since first, we designed a unique optimization layer for both contour and trajectory planning. We derived an algebraic condition of a collision check which allows accuracy in representing obstacles as polytopes, being these obstacles have an arbitrary shape, and the aggressive maneuver capability to become the obstacle avoidance process more efficient, allowing the aircraft to fly through narrow gaps and performing deviation maneuvers whose success depends on the attitude of the UAV. As our future works, we intend to extend the proposed NMPC for a robust formulation to analyze the controller stability and test it in real experiments. I would like to thank NMPC, CAPS, SAC, PAPESP, and FAPEMIG for all the support. As well, I would like to thank for your attention. That's all. Thank you very much. Any questions?